Hello everyone, this is Mr. 13 Things, and today we're going to be talking about a number of things, but mostly we're going to see how quickly we can go through perhaps a precursor to learning the unit circle, and that is me processing what my daughters have done. My daughters are 7th grade and 10th grade at the moment. What they've done pretty much every year since they've been through elementary school in math class, and that's dealing with shapes and geometry. That culminates at some point with a class called geometry, which is a freshman or a sophomore year class, and then analytic geometry. But the reality is, you can tell from the elementary instruction that many people know that these things are related, and they don't really close the loop for students. So what we're going to do here is we're just going to kind of close the loop a little bit and work backwards in terms of how the unit circle works. I want to point out that I'm recording on an iMac using Windows, and I'm using a program called Camtasia. There is an open source program called Cam Studio, which is easily downloaded, and I'm using something called Smooth Draw, mimicking as much as I can what Sal Khan does, for a number of different reasons, but mostly because it is open source and or reasonably priced. So I've got here's an open white screen. I'm going to just show you. I got my pen here. Whoops, that shouldn't work. Edit, undo. All right, so I'm just going to basically write a little bit up here. You can see that I'm writing, but because the one thing this program does not have is a good circle tool or a good line tool, I'm going to go ahead and import by going to right here. I've got you'll see off on the left, I can't show it to you, but I've got a set of layers, and I'm going to go ahead and import a layer image, and you're going to see how badly arranged all of my files are. And I know I'm going to call this one, this is the base circle, and I'm going to bring that in, and I'm going to move it to where it needs to be, and in a second I'm going to click up here and stop there, and so I have a base circle. This circle, if you recognize it, has 24 slices, and essentially it probably should most look like perhaps something like, I don't know, a pie with 24 slices. From this vantage point, it might also perhaps be what a computer model would get you if you were basically looking at a cone in 3D. So this idea of a cone with something like that, all right? See how bad my sketching tools are. So that might be any number of things, but what I'm going to talk about it being is basically a circle. And what I'm going to do right now is I'm going to leave some of these lines in here and erase out the rest. I apologize if this is going to take too much time, but I can set my brush size, and I think I can set my ink flow, and I am in the eraser. So I can go ahead and I'm going to erase out pretty much most of what it is, just so it doesn't deflect from your eye. So I'm erasing. And what I'm going to leave up is the ones up here. They're a little bit highlighted in the first quadrant. I wish I hadn't erased the center point, but that's fine. Obviously the center point is where any of these lines come through. And this is... Alright, so what we're going to talk about now, before we get into actually the concept of trig values, right, trigonometric function values, we're going to talk about how you can inscribe any polygon inside a circle. So for that reason, I'm going to go ahead and turn to green, and I'm going to say, let's say I want to point a polygon, a rectangle that's inscribed in a circle that includes that point. And basically all you're going to do then is you're going to draft up, see if I can do this poorly, a line that way and a line this way. Right? And it's not going to be a rectangle unless this is at 45 degrees down here. And then you're going to do what I would call the reverse pool shot. A great way to do this is in a program called Algoru, and that uses a laser. It's basically, this is what a laser will do if you shoot that. So you've basically sketched up that polygon. So the basic concept here is pick any one point, and we'll leave it with this one here. And what kind of questions, I'll leave the 0 point there, what kind of questions would you have asked in elementary school? Well, one might be, well, what is the area of that? In the end, what I'm trying to target is how do you get the coordinates x and y, or if you would, in a vector form at x and y of any point on the circle. And what you will find is this. The coordinates of point 1, the magnitude of the coordinates of point 1 are the same as the magnitude of the coordinates of point 2, or actually 3, 4, or 5. And so that general concept of having students play around and inscribe a rectangle inside of a circle is something that has huge ramifications, and we'll see why later. But the fact that it has huge ramifications because it really gets to the point of how you can determine the sine and the cosine of any angle, theta, and I'm going to kind of draw that line there. So basically the angle, if I looked at the angle here, right, that angle theta, its sine and cosine are equal to the x and the y values of that with essentially then a positive or negative value thrown in. You will not see it taught this way, and I'll do a better job perhaps in the next one, but the fact is, if you want to know the magnitude of the cosine and the magnitude of the sine of any point on the circle, you draw the inscribed rectangle and then take the values here. And so it turns out that on a unit circle, this is assuming that this is a unit circle, which means that the radius is 1 and the diameter equals 2, which is redundant information, but getting students to do this right away. And actually the area, I'm going to talk about that too, area equals is pi, and the included angle equals 2 pi. So all this information is true of the unit circle, and it all becomes incredibly important as you try to use a number of the unique properties of the circle, unit circle. All right, but that said, what is an interesting thing one could do with kids, however? So what in fact might be one way to figure out the area of this rectangle? And one, you might see this. You might see that this basically is a rectangle that's basically this triangle flipped over. And this triangle has a value of the x basically equal to cosine, and the value of the y equal to the sine. These, of course, are both negative. Here in this quadrant, it is negative in the x and positive. In this quadrant, they are positive in the x and negative in the y. And in this quadrant, they are positive and positive. So by splitting out the magnitudes and basically the sign, if you would, or the direction of the sines and cosines, you can see pretty quickly that the area of the entire rectangle is just 1, 2, 3, 4, 5, 6, 7, 8 times the area of that. So the area of this rectangle is going to be 8 times the cosine of theta times the sine of theta. So the area of the rectangle. So you can kind of get the sense that earlier in the classroom instruction, one could go through first doing two things. First, drawing in, I'll change the color now here, drawing in any point anywhere on the circle, right? So that point becomes that rectangle. Bad case of no line. That one becomes that one, right? So full knowledge that if you get a point and any point on the circle, even to a point here, we'll do the last one here, we'll change the color. If you pick any point on the circle, you can find the point in the first quadrant, which has the same magnitude as the point of any other one on the circle. Later on, you will find there is even more uniqueness going on inside the first quadrant with a line of symmetry at the 45-degree angle. There's a symmetry line there. There's more uniqueness, but if you start with the fact that you can draw inscribed rectangles from any point in a circle with lasers or with whatever you want to do, to get the fact that all you really need to learn in trig to kind of understand it is concentrate on basically the points regarding the angle of 0, an angle of pi over 12, an angle of pi over 6, and an angle of pi over 4. So If one hears me, 4 points on a circle, 4 points on a circle, how hard can that be? It relates to the fact that you can get any point, the value of any point on the unit circle, by doing a little simple geometry and sketching or doodling and coming up with some value in the first 45 degrees of the first pi over 4 of a circle. So this then is something that we can go ahead and do a draggable quiz on. So I'm going to go ahead and do that, and what I'll do is I'm going to just basically tie that and link that into this video. The point of this video was basically inscribed rectangles. Inscribed rectangles in the unit circle. And eventually you will realize that one of the key things that relates to this is the fact that any circle is the unit circle made smaller or larger. So you're very quickly able to determine some values on any circle if you know its center and its radius and an angle. So the point is, you can go ahead and pick any point on a circle. If you draw the inscribed rectangle, the magnitudes of the x and the y each, or the sine and the cosine, if you will, of all the points that touch the circle is the same. Thanks for listening.